notice that even though usually in OChem we don't draw the hidden hydrogens, for obvious reasons when you're doing NMR, it's an excellent idea to draw in the hidden hydrogens because we're focusing on the hydrogens. How many peaks do you think we're going to get here?
Okay. So those are two methyl groups at the top.
Yes. Oh, so which means I forgot they have hydrogens too. Do I really want that? I guess there's no way to go like that. Well, let's try this. Let's get rid of those methyl groups and replace those with fluorines. So how many peaks would we have here?
So carbon, okay, let's see, those will be the same. I'm gonna say one.
One peak? Now, are these hydrogens equivalent to these?
No.
No. For one thing, these are closer to the fluorines.
Right.
Any difference in the environments is going to make a difference there. These are closer to the fluorines, so even though these are both on CH2 carbons, these are going to be a different group over here. These would be the Bs. Could I call these the Bs as well? Yeah, that's fine, because these are both the same difference from the same distance from the fluorines. And how about these? Would these be A, B, or C? So how many peaks? Three. This is the first time I've put in a non-carbon or a non-hydrogen. And notice that when you do that, that tends to give you less symmetry. For example, now the top of this molecule is different from the bottom. So now it matters who's closer to the top, because the top is different from the bottom here. So all the problems I've given you so far were probably too easy, because you're going to see lots of examples with non-carbons and non-hydrogens. So we have to start seeing how to deal with that. So here we would get 3 peaks. How many peaks here?
3.
Good. How many peaks here?
Is that CH3, CH2, CH3?
Right.
Those are the peaks. Okay, so the hydrogens on the first carbon and the last carbon are going to be the same.
So we can give those the same letter.
Right. 1 peak.
So these are equivalent. Now are they equivalent to the hydrogens in the middle?
Hydrogen will be attached to a carbon that's attached to CH3. Oh no, they're going to be different in the middle though.
The easiest way to see why they're different is these are on the ends and this is in the middle. So that gives us 2 different environments. If you wanted to say more, you could say these hydrogens are on a carbon attached to a CH2, but these hydrogens are on a carbon attached to 2 CH3s. But it's probably simplest just to say this is in the middle and these are on the ends. So those are different environments. So this has to be given a new letter B. And how many peaks would we get?
2.
It's important to compare these 2 examples. This has 3 peaks, but this has 2 peaks. Why does this have more peaks? Because in this case, the end hydrogens are different, whereas in this case, the end hydrogens are the same. And why is that? Because putting it in the fluorine destroyed the symmetry. As we said before, the more symmetrical the molecule is, the more similar hydrogens there are. But when we put in the fluorine, so down here, there's no difference between being on the left-hand carbon and being on the right-hand carbon. So the left-hand carbon and the right-hand carbon are equivalent. But in this picture, there's a big difference between the left hand and the right hand carbon, so they're not equivalent. All right, now what we've seen is different connectivity means non-equivalent, and same connectivity means equivalent. Now, unfortunately, there are some exceptions to this rule over here. There are some cases of hydrogens that have the same connectivity, but are still different. Usually the same connectivity means equivalent. Unfortunately, there are some exceptions where the same connectivity means non-equivalent. Now, whether or not you need to know about those depends on how hard the problems are that you're seeing. So as we'll take a look at some of the sample problems here, and we'll see whether we come across any of these exceptions or not. We'll only go over the exceptions that he specifically included, because some of these might be harder than he expects you to know. But it is good to know that there are exceptions where things with the same connectivity can really be different. So we'll see whether we need to know about those. Well, let's try to working through this example. Let's try to figure out how many peaks we would get here. And a good approach is the labeling method, putting a different letter near the hydrogens that are different and the same letter on the hydrogens that are the same.
Okay. So all of the hydrogens attached to this carbon at the end are going to be A. And then the hydrogens on the second carbon are attached to a CH3 and a CH2 and an NH2 on the third carbon. So, okay. They're all going to be different.
So how many peaks?
4.
And we can put in these letters. Good. Now the easiest way to describe the difference in connectivity is simply to say these hydrogens are furthest from the nitrogen. These are closer to the nitrogen, and these are closest to the nitrogen, and these are on the nitrogen. That's all we need to do to describe the fact that they have different environments. So you're right, there's 4 different peaks. Let's try this example. How many different peaks?
Okay. The hydrogen at the very top will be A.
Good.
The hydrogens on the carbons most closely to the end are going to be B.
Good.
And then, using the method used for the previous problem, I would say that the ones on the bottom are C. I'm not.
So how many peaks?
3.
Because the left and the right hand sides are equivalent. Good. Okay, that's right. These are different. B's are different from C's because the B's are closer to the nitrogen. That's really all we have to say to show that there's different connectivity. These are, so this is connected to a carbon that's connected to a nitrogen, but this is directly connected to a nitrogen. That's all we need to say to show there's different connectivity. So I think you said 3 peaks, and that would be the correct answer. Good. Let's identify how many peaks here.
Okay. I would put the carbon on the far right.
Go ahead and put in your letters. So it looks like you said these 2 are equivalent?
Mm-hmm. I want to change that.
Okay. If there's any difference in their environments, then they're different.
So this will be A, B, C, D, and then
And whether, again, whether you actually should draw in the hydrogens, I guess that's a matter of taste. Maybe it helps to draw the hydrogens, or maybe it's confusing to draw in the hydrogens. You have to decide on your own. I'm not going to draw the hydrogens in here, but these hydrogens are all different from each other. Now, at first I think you thought that these two sets of hydrogens were the same, but the reason that they're not the same is that these hydrogens are on a 2-carbon chain, and this hydrogen is on a 3-carbon chain. So even though they're both right next to the oxygen, there are differences in their environments. These hydrogens are on a 2-carbon chain, and these hydrogens are on a 3-carbon chain. And then this is another carbon down here, and again, the E carbons here are not the same as the A carbons, because this is at the end of a 2-carbon chain, and this is at the end of a 3-carbon chain.